Good afternoon, everybody. Welcome to this week's Heidelberg Joint Astronomical Colloquium. It's a hot holiday Tuesday afternoon, but you know where the blessed places be, and especially since we have this week Angela Adamo, who's going to tell us a lot about galaxy evolution from the observational perspective. So to introduce Angela, I will ask Catherine.
All right. So it's my pleasure to introduce Angela Adamo. She did her master's degree at the University of Padua and then her PhD at Stockholm University on star clusters in blue compact galaxies. In 2011, she came here to Heidelberg and she was at MPIA as a postdoc fellow. And then in 2014, she went back to Stockholm, first as a postdoc fellow, then as a research group leader. And finally, in 2019, she started as a professor there and was recently promoted to associate professor. She's been very successful in getting a lot of grant funding and telescope time. So she got an establishing grant from the Swedish Research Council. Her work has been focused on star clusters and stellar feedback, both locally and across cosmic time. And so she's been pursuing a lot of observational studies with the VLT, with HST, and now more recently with JWST, where she's had two very exciting GEO programs approved in cycles 1 and 2, which we will hear about today. So thank you.
Thank you, Catherine. Good afternoon, everyone. It's really strange to sit on this side. So there is hope. If I'm standing here, you all will be standing here as well. And yeah, it's a pleasure to be here. Thanks for the invitation, Catherine and Richard. And today I will be talking about star cluster formation, feedback, and evolution across cosmic times. And usually this is my favorite topic, but I have to say that since December 2021, when JWST finally, the rocket liftoff, it has been really an adventure even more. So here you see we were watching with my family the launch, and you see Christian turning around because he thought he could see the rocket actually from the window. Of course he couldn't, but it was really amazing. So since then, we have stopped sleeping, looking at data, waiting for the data. And I would like to start with this fundamental question that I think all of you ask yourself when you apply for grant and when you plan your research. Where do stars form? And so before JWST, we were already used to see simulation. This is a simulation of an isolated disk galaxy where we could see filamentary structure in the ISM. We could see spiral arm enhanced in star formation. And if we zoom in, we can see the shells produced by feedback where stars are forming. But I think that these astonishing images from these are beautiful images from the FANCS program, the large program, which was approved in cycle 1, one of the first images which was released. And you see how we have revolutionized the study of galaxies just with a single image. It's really astonishing, the details that we can look at. Here you are looking at the ISM, warm ISM, at around 100 Kelvin, showing us bubbles, filaments. The bright dots here, if we want a comparison with what we were used to see in the Milky Way, are young star-forming regions where stars will form in cluster and their feedback would start to push away the leftover gas surrounding them. So why we are interested in clusters? I think that this simulation by Rowe and Smith in 2020 are quite impactful. Just visually, you see here on top that if you don't add clustered feedback, your galaxy ISM doesn't look like what we are used to. You see very long filamentary structure that then don't look at all what we are used to. They don't look like the fragmented image that you can see at the bottom in the zoom in of the clouds. And indeed, again, this is NGC 628. In this beautiful press release image, you can see that clustered feedback really matters. And in general, stellar feedback matters in all natures. Again, I'm borrowing from simulation, but the rest of the talk will be about observation, so don't fright. Here you see that the top left plot is a zoom in into a star-forming regions. We are looking at roughly 200 parsec in radius with no feedback. The ISM doesn't look like reaching the temperature that we are used to see when we do, for instance, temperature estimates from MUSE data. And when we add the supernovae, it's not enough. Supernova exploding in a medium where pre-supernova feedback photoionization has not been operating would not make the impact that they usually do, and we see in observations. So you need both feedback, and this is the bottom right plot, to create a multi-phase ISM. And this is indeed is confirmed then when the author of this paper showed the space phase diagram for temperature and density. You see that in the right plot, essentially when you add all the feedback, you get the right structure in temperature and density that you expect from the ISM. So multi-phase ISM, but what do we want to do? So in this talk, I will mostly focus on the emergence phases of star formation. So we are going to look at a few parsec scales, so 10 parsec scales, where we have early stages. We have molecular clouds, which are gravitationally self-gravitating, and their gas is quite dense and the temperature are very low. And then once they start to collapse and form stars, we can follow up. Feedback from stars create H2 regions. These are quite compact, but you see it's reprocessing the ISM, the feedback from the stars is creating a medium which is 10 to the 4 Kelvin in temperature at densities which are at 10 to the 2, 10 to the 3 per cubic centimeter. And then it's surrounded by still what we call a PDR, photo dissociation regions, where the temperature are 100 Kelvin, so warmer than molecular gas, but density are quite high, so 10 to the 4, 10 to the 6 particle per cubic centimeter. And then finally, we reach an exposed phase where stars have managed to carve the ISM, have managed to destroy most of the PDRs. And then these are the region essentially that we see mostly in the optical. So when we see the open blister H2 region with the stars inside and clearly connection between the two. So the fundamental question I want to ask today is how long it requires for the stars to create H2 regions. And that question becomes, how long does it take for stellar feedback to destroy the giant molecular clouds where it has formed? This question is quite fundamental because it sets the star formation efficiency in the cloud, so locally. It determines the lifetime of molecular clouds, and it determines also the shape of the ISM in terms of density, of energy, temperature. And it's really important because it regulates how much stars will form next. So it regulates the star formation cycle. So for the early phases, we can look at giant molecular clouds properties. I will not have time to cover all the properties that describe macroscopically giant molecular clouds population. But for the connection with star cluster, I like very much to compare the giant molecular cloud mass spectrum in the local galaxies. So here you see this is M83 with the CO mapping at roughly 40 parsec resolution. And we see that when we look at the giant molecular cloud mass spectrum, this is the top plot and the bottom one. And what you see is variations, not much in the power law part of the giant molecular clouds mass distribution, but the very end. So where clouds are forming will determine what's the most massive mass in the clouds that you get. And this is very important because when we look at star cluster population, this is now a recent plot from Weiner et al. In 2022 for M83 star cluster population. You see that also the star cluster mass function is not really well described by a power law. So you can look now at the observed cluster mass distribution is in black, and then the red is the power law function, and in blue it's a truncated power law, truncated at a characteristic mass. And what you see is that, so to describe the mass function of local galaxies, you need this cut. Otherwise, you would over-predict the number of very massive clusters, you see? So if you assume a pure power law, and you sample the same number of clusters you observe, you should have determined at least a factor of 2 more massive clusters than you actually observe. And this is not only for M33. This is for other local galaxies. It's just, it's not a dramatic change in the physics. It's a power law -2, but we are describing the probability of forming massive cluster in local galaxies with this function. And that you can do for other galaxies. So here you see this has been done for many other systems. And what we see essentially that there is a connection between where star cluster population are forming and the gas surface density of the galaxy, with the maximum mass, this characteristic mass or truncation mass, scaling with the star formation rate density of the galaxy. So essentially galaxy with higher star formation rate, which would imply also higher gas surface density, have a higher probability to form massive cluster, okay? And this is true in general, although for local dwarf, I have to say that we haven't been looking so far, and we do not get truncation. And this is because if you see dwarfs cover a large range in star formation rate densities, but their population number is very low. So to statistically get a significancy, you need to sample many dwarfs. And so we are actually working on that. And then recently with a chat with Adam and Eric, I asked them, have you ever plotted the truncation mass for the giant molecular clouds as function of star formation rate density in the galaxy? And as you see, the correlation is not as nice because it's not a one-to-one correspondence, right? Molecular cloud cluster, but also the maximum mass in the molecular clouds population seems to scale with star formation rate densities. Again, linking how much gas, molecular gas is available in the galaxy and what maximum mass you can form. Finally, in the quick introduction of star cluster properties, I think it's interesting to look also at the cluster mass and sizes of star cluster. And in general, so if you, I think you know, giant molecular clouds have a mass size relation which scales as 1/2. For the cluster, this relation becomes much flatter. And in general, if you plot the sizes, they take a log normal shape with a peak at roughly 3 parsec. So we are moving from clouds which are 40, 50 parsec across down to very small scales. And these are the stellar surface density of clustering local galaxies. So here on average, we see, these are many galaxies actually, for which sizes have been estimated. The average star formation, stellar surface density of cluster is 200 solar masses per parsec square. And if we want to give you a comparison, globular cluster, which are roughly 10 to the 5, it's the peak of the mass function, right? 2 times 10 to the 5, and sizes of 3 parsec have a stellar surface density of 10 to the 3. So much more denser than what usually are a local cluster. So then what we can do We have been looking at the emerging phase. We have been looking at star cluster population. We can actually see globular cluster. This is a plot from Forbes and Bridge in 2010, where they plotted the metallicity of globular cluster in the Milky Way as a function of their ages. And you see that they line up in a kind of a Y shape. And actually what we can say is that this globular cluster, what we think is happening is this globular cluster are globular clusters that formed in the progenitor of the Milky Way. So we call them in situ, while the globular cluster traced by these other lines are showing you the family of clusters that have been accreted. And we can follow this, for example, with cosmological simulation, where globular clusters have been added. So I show here a picture from the mosaic simulations, but actually there is a huge literature about implementing cluster population formation in galaxies. And you see that essentially clusters follow the star formation history of the galaxy, the assembly history of the galaxy, and they also survive in a certain amount. So there is quite a huge, rich information constraint in globular cluster population for galaxy assembly. So this we can do it either numerically with cosmological simulation, or nowadays we can use lensing. And when we do use lensing, essentially the gravitational potential of galaxy cluster bend the light of background galaxies and stretches and magnifies this light. And that enables us to actually probe tens of parsec scales at high redshift. And so here I show you the sunburst arc. This arc is quite remarkable. The galaxy, the real image of the galaxy is a bright dot over there, which you will see it. There is actually, oh, sorry, this is, it's this bright dot here. But then, so what happens is if we zoom in, we see that there are many images. So here you see there are, if you count the brightest spot, there is 1, 2, 3, 4, 5, 6 images of the same galaxies. Actually, lensing is really amazing. And if we take spectra of this object, so we see that we are looking at a star cluster which has far UV light that overlaps with the far UV light of R136. Exactly, so it has massive stars, it has stellar winds, it has absorption. So these are P-Cygni lights from stellar winds. And you see 10 to the 6 solar masses, 10 to the 7, 3 million years over a size which is roughly 2 parsec. So I have to say that sunburst arc is a quite remarkable laboratory to study Lyman alpha escape, also Lyman alpha emission, and so on and so forth. So you really start to see the link between star cluster formation and galaxy assembling and growing. This is a very complicated picture, don't worry, but essentially it's showing you that there are several images and the magnification is growing, and here we are probing very small scales. Now with JWST, we can play this with much more details. This is the sunrise arc. It's a very complicated naming. This is the same galaxy which has been imaged 4 times. 1, 2, 3, there is a partial image here, and 4. And what we see, this is Ehrendal, it's a single star, a ratio 6.2. How amazing is that? And we see star cluster, here 1 parsec, look, sizes of 1 to 5 parsec, quite young ages, and stellar density, they are even higher than globular cluster. So we are looking at globular cluster formation at the age of reionization. But globular clusters are complicated creatures. They are chemically quite complex. So you see here there are anti-correlation. between chemical elements, which have been suggested to be different. They are called also multiple stellar populations. So first generation, second and third population, all within 3 parsec. It's quite amazing. And this multiple population of chemical complexity seems to be somehow connected to the age, so up to object deformed roughly redshift 0.6. And then it seems the local, more recent massive cluster do not have this population. So in this talk, I will not discuss multiple population, but clearly we can look at the places where this globular cluster formed. So this is what I will cover. So quickly, we will go through the emergence phase of young star cluster. We will look at cluster feedback in local galaxies, and then we will discuss the clustered star formation at high redshift. So for the hidden phases, or we can call it also the emerging phases, we will look at data from the JWST program called FEAST. And the motivation for FEAST actually has been a huge investment from JWST Optical, where we have looked at optical morphology of H2 regions, and we have tried to use this morphology to actually determine how long cluster stays embedded and how long this embedded phase lasts. So here you see from JWST optical based studies, but also from inference studies, so using a bit larger, so 100 parsec resolution data, it seems that this phase seems to last between 2 and 5 million years. But what near infrared, so how far we could do before JWST showed us, is that actually we miss a lot of embedded sources. So the FEAST program was created essentially to discover this embedded phase and determine the timing for the emergence. And we want also to map the evolution of photodissociation and H2 regions. We do that with the different tracers. So this is the sample. I will present the tracer in the next slide. But this is the sample of galaxy. We sample the main sequence. We have one target across different mass ranges and star formation rate. We cover also a fair amount of metallicity range down to 8.2. And the filters essentially cover the near infrared in broad bands. And we added also narrow bands which cover the Paschen alpha and the bracket alpha 4 micron. And we have also medium bands which cover the pH emission at 3.3 and the pH emission at 7.7. This is the sample with JWST imaging, and the footprints show the JWST data. And the first data for this galaxy arrived in July last year, but we got Jupiter on the way. So we had a problem with the persistence, and we didn't manage to do much with the data, but actually in January, the data were retaken. Here you see an image of the mosaic we have, and I'm showing in blue the continuum, the light of the stars, while in 3.3 and in green, and the Paschen alpha bracket alpha emission in red shows essentially the regions where H2 regions are. And this shows the region where pH emission is. And you see the filamentary structure of this gas. 5 weeks ago, we got M83 data. Sorry that I'm flashing up images. They are really beautiful. We are working continuous subtraction for the narrowband is still on testing. It's proved to be not so easy. So, but when we zoom in into regions, you clearly see the filamentary structure. You see how compact star formation is happening and how permitting is the pH emission, even at the 3.3 micron. So for the rest, I will focus now on the galaxy where we have done the most advanced analysis. So here you see the footprint of the JWST data, and we have analyzed the cluster population within the entire footprint. But here I focus especially on the JWST area. And we have recreated a new cluster catalog, including also the JWST data, including narrow bands. And you see now that the age distribution align quite closely to the models. So we see young cluster, intermediate age, old cluster throughout. And we use this optical catalog to time the scale, these timing scales I was talking before. So when we look at the JWST data, then what we do is we look for where the embedded star-forming regions are. I will tell you in the next slides what these little dots show. But in spite of their color, these little dots are showing you compact sources in NGC 6 to 8. And you see, so here I show the contour. The 3.3 is much more extended than the Paschen alpha emission, as already we saw just looking at the data. And here you see the CO maps we have available for this galaxy, where star formation is happening, and the CO at the same location. So if we look now, let me show you what this color means. Essentially, in red, we are finding sources that have a peaked emission, so they have a compact emission in Paschen alpha, bracket alpha, and 3.3 micron. In orange, we look at sources that have you don't see the compact, so the continuum, because these are continuous subtracted data, but essentially we see the compact emission in the bracket alpha, Paschen alpha, but the 3.3 micron has disappeared from these regions. And in green are these compact sources at 3.3 micron that do not have a counterpart in emission. And then finally in blue, you see where are the compact cluster previously detected. And you see sometimes they overlap with the cluster and some with this emerging star cluster we are detecting, sometimes not. If we look at mid-infrared color, now these are just JWST color, you see that all the regions we have extracted aligned on this specific area of the diagram. And if we look at median colors, it suggests that the young star, so the emerging star cluster 1 are more embedded, sitting on top of hot dust, which is transmitted by this filter, and having higher extinction, while the embedded star cluster 2 are already moving. So we see an evolution sequence. The 3.3 micron remain a bit of a mystery. So this is kind of a low resolution spectroscopy. We are using all the bands available for the galaxy, and we are plotting average SEDs. You see that the red ones are the most extreme in all the emission. The yellow, you see already more, so their extinction is lower. The line ratio go down, so suggesting lower extinction. And the green one are quite puzzling. They have the continuum light that overlaps a bit with the embedded young star cluster 2, but they don't have so much emission in the lines. And they seem to have a much more extinction when we go to bluer bands. So we think that this 3.3 micron peaks could be either deeply embedded cluster that have not yet had massive stars reaching the main sequence, or they could be low mass cluster, which actually did not form massive stars. So they do not have emission in Paschen alpha, bracket alpha. So if we look a bit of statistics, what we see is that roughly 50% of the emerging star cluster lie in the category where we see coincidence in all the tracer, and 50% do not have any more 3.3 PIH emission. If we look at the bracket alpha, which is the longer wavelength we have in the data tracing ionization, then we see that only 8% of the bracket alpha peaks, we detect them without Paschen alpha. So, and maybe these are the really embedded one we are still investigating. And then we see that again, 50% of the 3.3 micron extracted have coincident with the emission lines, so have massive stars. They are in the same regions at a few parsec scale, while 40% not. So if we summarize a bit, what we see is that we have a very short embedded phase, which becoming quite soon evident in all the tracers we get. If we combine the emerging star cluster with the optical one, we see that there is only 35% of coincidence, but for this 35%, we can derive that roughly this age is between 3 and 5 million years. So at 5 million years, all the clusters we have in the catalogs are detected optically. Okay, and finally, Alex, a PhD student in Stockholm, is looking at the H2 region and PDRs. So here you see distribution as function of galactocentric distances, of sizes and flux in the H2 region in PDRs. We clearly see differences. PDRs are much more extended, and we see also differences in where we are in the galaxy, with the outer bin coinciding with the second co-rotation radius, having more extended and more luminous H2 regions. Alex is also looking at the coincidence of surface brightness in the H2 regions. So we start from Paschen alpha, we take regions that have a peaked emission in Paschen alpha, and we look at how the other tracer behave, in particular the 3.3 micron. And we see that we find regions where all the tracers are peaked, while we find regions where the 3.3 micron is deficient in the center. And we try to coincide this with comparing the slopes. So here it's the slope of the 3 micron becoming increasingly positive versus the slope of the Paschen alpha, which is always negative, so it's always peaked. So there is a clear evolution and disruption of PIH. So I will now move a bit into stellar feedback connected to star cluster. And to do so, I would like to kind of name the type of feedback. So when we look at stellar feedback, we focus on massive stars, so more massive than 8 solar masses, and short-lived, roughly 40 million years, up to 40 million years, then they are all gone as supernovae. They produce UV radiation. This UV radiation causes radiation pressure and photoionization in the H2 region. They produce stellar winds, and this is mechanical energy producing shocking the H2 region, and also producing metal enrichment. And of course, they explode as supernovae, so the mechanical energy injection continues from 3 million years on. So to quantify pre-supernova feedback, it has been used in the literature, what we call a pressure term analysis. And we look at the pressure, is called ionization pressure or H2 region pressure or thermal pressure, essentially express the kinetic and pressure in the H2 region exerted by photoionization. We can look at the direct pressure, and this is how much momentum the photons have within the H2 regions. And that momentum, since it collides with the walls of the H2 regions, creates also expansion. And we can look also at the amount of escape radiation from H2 regions. So if we do that as a function of stellar cluster properties, we see that the direct pressure and the ionization pressure is relates to the cluster age. But this correlation lasts it's very short, up to 2 million years, and then it flattens out, suggesting that star formation taking place around the cluster is probably taking over and maintaining the ionization pressure. And if we look at the term as a function of total mass of the cluster, you see that there is a clear relation, which with the more massive cluster, putting more pressure in H2 region. We have compared these pressure terms with the pressure in the ISM of the disk. And so you see we have combined them is this black empty dots, and while the disk, the ambient pressure in the disk is the green stars. And what we see is that in the case of M83, H2 regions are expanding already from simple pre-supernova feedback, and we have not accounted for all the pre-supernova feedback. So photoionization is enough to make H2 region expand, while in the center of galaxies is another story. So H2 region, pre-supernova feedback is probably not enough. So what we find instead when we look at escape fraction is that star clusters do not seem to lead escape fractions. We see a positive signal for very young ages, younger than 2 million years, but then the escape fraction is going down. So star cluster, we know there is escape fraction because we know there is a warm ionized medium that needs to be powered, but it's not the star cluster that are doing the job in this case. And finally, in a recent work done by Mattia, who is defending his PhD in 2 days from now, we looked at outflows using far UV spectroscopy. Now you see that we look at star cluster with the cos. So this is a circular aperture, it's a far UV spectrograph on JWST. And what happens is when you look at a far UV background source passing through the ISM, then it imprints an absorption feature, which has a static component and a blue shifted one. This blue shifted one gives you the amount of outflowing gas due to the feedback from the star cluster. So we have done, here you see the atlas of the spectra, quite beautiful. Far UV spectroscopy has a lot of information in terms of stellar population and ISM. And when we look at correlation, what we see is that we see outflow gas in the spectra, and the velocities of the outflow doesn't correlate clearly with age. There are some trends, but these trends are not clear with the age of the young star cluster, while it clearly correlates with the mass of the young star cluster. So more massive is the cluster, faster outflow can be driven from the H2 region. Then you see, I'm sorry, probably you are not able to read it, but this is the stellar winds. Also there is a correlation. And supernovae, although not many regions have had a lot of supernovae, so less than the entire sample. But when we combine the two together, again, this correlation is quite clear. You need the mechanical energy to drive outflows. Yes, and finally, we compare these outflows from star cluster to galactic scale one. And here in the black, we plot the data from the literature, as well as CLASSE, which is a large far UV program that has sampled the starburst galaxies or low metallicity galaxies. And you see that star cluster follow kind of the same relation with that has been proposed in the literature. So these are the black and red lines, but the normalization is different. And indeed, when we look, instead of a star formation rate, we look at star formation rate per area, we see that this offset is gone. So star cluster outflow behaves like mini galaxies, or the other way around. We can say the outflows in galaxies are a kind of are a scaled outflow from star cluster. So in the last 10 minutes, yes, I will cover the final part of the talk, and it's about connecting star cluster formation with the high redshift universe. And here this work has been done in collaboration with Adelaide Clesson and Chris Asher. So to To introduce you to the high redshift, we need to make a few considerations about how star formation is operating at these scales. So this is a plot which shows the molecular gas fraction in galaxies as function of star formation history of the universe. And we see that there is an increase in this gas fraction. If we look at the main sequence of galaxies, we see the galaxies at higher and higher redshift form more efficiently stars per unit mass. And finally, their disks are highly turbulent. So here it's a plot of the rotation velocity versus the velocity dispersion that goes actually, it becomes so these disks are dispersion dominated. They are highly turbulent. They are marginally stable. So they are capable of forming clumps. And there is a huge literature about it that I cannot cover today. But I can say that when the first JWST images were released, was 12th of July, I was sitting with Adelaide, and this galaxy here, this little object, captured my eye. And so this is called the sparkler. We are looking at a galaxy at redshift 1.37 with the globular cluster already in place. And I found this quite amazing. So we start to look at the data. Here you see we extracted all the clumps in the galaxies. We extracted the globular cluster. The sizes are also coincident with being really compact object. You see the ages, they are quite old. So we are really, if you want to kind of imagine in this simplified history of the universe, we are looking at, we are at redshift 0, right? We are looking at a galaxy where is the blue line. And then we are looking at objects in this galaxy that formed 12.8 billion years ago. So there were two studies appearing in the literature. And you see here, I'm plotting the metallicity age diagram that I introduced before. And I'm plotting the Milky Way cluster, the Magellanic cluster. And you see that in the two studies, there seems to be a kind of dichotomy. One study suggested that these were all metal-rich globular cluster, while in the study we did, we found the metal-poor globular cluster becoming increasingly more metal-rich. So we went back and looked at the data, and this work has been done in collaboration with Chris Asher. He's actually an expert in fitting globular cluster in local galaxies, and he converted this software to fit globular cluster at high redshift. And we see essentially a lot of scatter. So there is no clear convergence for the ages of this old globular cluster, but what is clear from the fit we performed, I don't have the time to show the corner plot, but they are here if you are interested. Essentially, we get a lower limit to their age. These are globular cluster are old and metal poor, while there is also a population of globular cluster that is younger and metal rich. So this is the comparison one-to-one in both analyses. If we use the same software to analyze the ACDs, we get the same quantities or within the 1 sigma in agreement. And we can look then at the age metallicity relation. We can compare it, for instance, with the EMOSAIC simulation and see that indeed there is a kind of trend with scatter where we see a metal poor population which is more metal rich. So we see a galaxy that is slowly assembling, and if we use again the simulation, we can predict that this system, so if you look at the dashed line, will become about an M33 disk at redshift 0. So, and then in the last 3 minutes, here you see, we are looking now with Adelaide at A2744. This region is quite amazing. So before JWST, people have looked only at this part of this galaxy cluster. And they predicted with the lensing and gravitational models of these regions that there was an overdensity on the side, but actually has never been looked at. And when the JWST data came out, I have to say, I'm not expert in lensing, but my colleagues were really, really surprised because there is not one cluster, but there are three. So you see 1, 2, and 3, and they seem to be interacting. So it's a huge region with huge magnifications. Here you see, we are looking at roughly 433 galaxies. We have 2070 uniquely identified clumps. So these are not multiple images of the same galaxies. This is quite unique. So far, this is an increase of factor of 10 in number of clumps that we are looking across this redshift range. You see here the average magnification are around 2, not too large, but still significant when we look at this redshift range, and we reach very high magnification, more than 50. So we are at parsec scales again. The galaxy we are looking at are typical of the main sequence in this redshift range. And so this is the study we did with a few hundred clumps in the first region that was observed with JWST. And now we don't need any more to sample data. We have consistently analyzed 2000 clumps equally distributed across redshift ranges. And we see here their luminosity and sizes. So we probe from 10 parsec scale to few hundred across redshift. What we see is that these clumps have a more or less similar mass distribution. If you look from the y-axis, the mass is pretty similar at all redshift, but their ages is not. So we are using the median ages are already changing. You see the cluster between redshift 5 and 4 are significantly younger than the clumps at redshift 1. And this is essentially telling us that the clumps that are forming here are surviving in their host galaxies. We also see a density increase in the clumps on average. So the dashed line shows the star cluster density in the young star cluster in a local galaxy like M51, M83. And the straight line, the solid straight line, shows the surface density, stellar surface density of a globular cluster. So what we see is that the clumps at hundreds parsec scales have a stellar density, surface density, that compare clusters. So these are really the places where star clusters form. And finally, before the conclusion, we see also trends with the galactocentric distances, where the most massive clumps and also the densest seems to be closer to the center of galaxy, again suggesting that these clumps are migrating. Okay, I'm done. Conclusions. Our initial JWST FEAST result have showed us emerging young star cluster a few parsec scales. We see that this population is quite significant. They rapidly evolve, and this evolution is suggested by their CD. Their extinction is lower, and their pH emission is destroyed. We have so far looked at one galaxy, but as you understood, we will look at more environment, and also to really understand the nature of this emerging young star cluster, I've secured cycle 2 niche spec data. So we are gonna get 1 to 5 micron spectroscopy of this object. We have looked at cluster feedback. It seems that in local galaxies, spiral galaxy, pre-supernova feedback is already doing the job of expanding the H2 regions on average. I told you that star clusters seem to not drive escape escape ionizing radiation from H2 regions. This is again connected to local spirals. It might be different for dwarfs. Looking forward to see this result. And there's also that cluster drive outflow from H2 regions that actually scales in a similar way to galactic scale outflows. And final, last but not least, we have looked at stellar clumps at high redshift, and essentially we see the star cluster in this galaxy is happening in regions that have much higher stellar densities, which would suggest why globular clusters are also so compact. We find also significances of, so that these clumps are surviving at least for a few giga-years within their galaxies and are migrating towards the center. And of course, so far only 10 galaxy cluster fields have been observed. We have looked at 2, but a lot of parameter space is there open for discoveries. So this is really fundamental for looking at star cluster formation at high redshift. And that's it.
Thank you very much, Angela. What a spectacular box and what a spectacular array of measurements you have. I mean, there are such interesting things in there. I'm sure that we all want to ask you about that. So I'll open the questions first to the floor.
Thanks for the talk. Maybe go back to the plot.
Yes.
It seems to me, if I look at the plot, that there are not really no more dense clumps I add redshift, but just less.
Yeah, so
Yes,
the bin,
that's
yeah, the red average contains up to redshift 5.5. So, and this is kind of the sampling of galaxies. So there are not many galaxies between this redshift and this, but nevertheless we have combined them. But so this part is included, and we have not yet looked at redshift 6 to 10, where we have still clumps. But yeah.
So yeah. My question was, how do we know that the lack of points in the low surface density is not due to the fact that they're just far away? So
yeah, so the low surface density are due to incompleteness, because as you get lower mass and the larger sizes, they disappear, right? It's a surface brightness contrast. So, but what is significant is the upper part that increases, because there we don't have a completeness issue on the upper part. So, and on average, then is telling that as you move to higher redshift, you find denser clumps.
Thank you. Any more questions from the hall right now? One next to me.
Thanks for the talk. I have a question for the CO map that you showed from NGC 628 with the star clusters. The star clusters are still embedded in the molecular cloud and have not yet completely destroyed the molecular cloud. So they would not give any feedback into this interstellar medium. What would be the time scales for the molecular cloud to be destroyed, so we would see a feedback from the radiation pressure of the star cluster to influence the interstellar medium?
So in this region, maybe we can focus on that one, is simpler. And I'm showing the CO contours. First of all, the CO resolution is much lower, so that we see a blob, but in reality, we don't know where the concentration of CO it is, because you see there is the center in the blue, right? So the blue center, it tells you that this star formation has already happened and has blown a bubble. And in fact, is one of the bubble Elizabeth has in her catalog. And then there is star formation as going on. So the cyan is already 5 million years old. And you do not expect to find CO on top of them, right? So the fact that you see this blob of CO is telling that there is CO, but we actually don't know where it is. And the idea is that is connected with the red circle and the orange one, so the cluster which are emerging. About the time scales, so what we see in this galaxy, we are fitting actually this embedded star cluster, but I don't have yet result to show you. But when we do the matching with optical, we see that it takes on average 3 million years before we start to see them coinciding with the optical cluster. Then it takes roughly 3 million years to open channels, and then that geometrically are aligned and we can see them along the line of sight, right? There is also geometry implied, but roughly 3 million years.
Another question?
Great talk. Sorry, I may miss. Could you please tell me what does the PH 7.7 line emission feature tells you about?
So let me ask the question that I understood. You ask what the 7.7 micron traces, or?
Yeah. So what does that feature tells you in when combined with the other data? Because I probably missed when you talk about.
Yes. So we have not yet looked at the 7.7 micron. So we have looked, but I don't have anything to show you right now. But essentially, the 7.7 pH band transmits, it's a reprocessed light from a mixture of dust grain sizes, while what we think we understand is that the 3.3 micron is some small dust grains. So it's a different, they reprocess different light because their sizes is different, and their size difference. So the mixture and the small size grains also seems to be connected to the strength of the ionizing radiation. So the small dust grains will be destroyed more quickly close to hard ionizing radiation than the intermediate one. But it's actually quite debated. So it's not as simple as I'm putting this, yeah.
Mucky business, the PAHs.
Yeah, okay.
No. I wanted to, if I may ask a question, because I don't see any more here. You had this intriguing statement about the variation of the maximum mass of the star clusters within galaxies. At least I saw that on some of the correlations, that the really massive star clusters were at the middle, the low galactocentric radii positions. And also, when you're looking at the galaxy population at all, you also see correlation with gas mass of the maximum mass of the star clusters. So my question is that the same correlation? You know, because you because you also mentioned that this star cluster mass was related, at least observationally, to the global mass surface density of the gas in the galaxies. So, I mean, those are quantities that you know for a lot of external galaxies, as well as within the nearby galaxies. And is this correlation of star cluster mass with gas surface density one correlation?
So, this is a very complex question. Let me see if I manage to answer. So the correlation between maximum cluster mass and star formation rate in the galaxy. So it's there. We have seen it for merger system and spirals. Is simply telling you that more fuel is available, higher is the chances of creating the condition for formation of massive cluster. Okay. Then the connection with the galactocentric distances that was done for the high redshift clumps, and that is different in the sense that these clumps we think that are either migrating because some of them are old and they are close to the center, but some are young and they are close to the center. The young one have formed there. They didn't have yet dynamical time scales sufficient to migrate, so they have formed there. But So
I guess I'm really talking about young star clusters.
young
yeah.
star cluster is not necessarily true that the most massive young star cluster is close to the center.
Oh, okay.
Like for NGC 628, which is up here, the most massive cluster in this galaxy is here.
Yes.
Actually.
Yes.
And it's
I
not,
always thought that
and
was
in the
I always thought
center,
that was an exception in this galaxy. but
yeah,
maybe we talk
no,
more about that afterwards.
there are more spirals where this is happening. And that again is connected to the dynamics of the gas in the galaxy. So you have to create conditions where there is a flows of gas are specific. So this is a co-rotation radius for the galaxy, and that's what was suggested in 2020 from the CO analysis, that there is gases flowing here and piling up, and
Okay.
therefore is creating more massive giant molecular clouds. But so there is correlation with star formation rate density, which suggests it correlates via the Kennigan-Schmidt law to the gas surface density of the galaxy, but there is no correlation with the distance from the center.
Okay.
On average, you see more massive cluster in the center, but those are due to dynamical condition. Bar bringing gas, center, sorry.
Yeah. Okay. Well, oh yeah, now Catherine can have the last word on this. Last questions.
Yeah, so the high redshift lens systems are amazing. I mean, it's incredible the spatial scale you get to, and that you're seeing these young, basically, I guess, forming clusters. So is there hope of doing sort of these pressure calculations as well for some of these systems?
The answer is, I don't know. We are getting, so I'm a co-PI for a program which is doing IFU NIRSpec spectroscopy of redshift 5 clumpy galaxies. So we will get exactly the same range covered by MUSE. And we will get the S2 lines and H alpha. So in theory, we should be able to do this analysis. And I will try to do it, I promise. But yeah, let's see how the data look like. It's a challenge. We have seen a very little NIRSpec IFU data for this high redshift clumpy galaxies. So fingers crossed we can do it.
Okay, well, I don't see any more questions. So thank you, Angela. And good luck with deciphering all this incredible data in the coming months and years. Thank you very much.